We were solving the eigenvalue problem, which is this equation right here. We've gone through that. And we needed to find two things. We needed to find all the lambdas that make this statement true, and then all the corresponding k's that make this statement true. Here is another form of the eigenvalue problem. And we went through how to find the lambdas. It was finding this determinant and solving for the lambdas, and we did an example of that. Other examples. Now let's find the eigenvectors. Here's an example. We already found those eigenvalues. And now here's what we have. Now we've got the lambdas, we've got the eigenvalues. So everything in parentheses here is just numbers. So you have a matrix times k, and we're looking for k. It's a 0 on the right, so we're solving a homogeneous equation. And we know we're going to get an infinite number of k's that work here, but not k equals 0. We don't accept k equals 0. So there's a couple ways to look at this. One is we're solving for the k's. We're solving a system of equations, homogeneous equations. But that's the same as finding a basis for the null space of this matrix up here. What are all the k's that make this statement true? That's the null space of this matrix. And there'll be an infinite number of them. So what we do, we plug in the lambdas we found. Okay, the first lambda was 0. Plug in 0 for here, you get the original 2, 1, 2, 1. Start doing Gaussian elimination. It's pretty obvious. There we go. It's in row echelon form. There's a pivot, a row of all zeros. And by the way, if you do not get a row of all zeros, you did something wrong somewhere. We're always going to get a null space of dimension 1 or more. And what does this tell you? That 2k1 plus k2 equals 0, or 2k1 equals k2. There's the pivot variable. Well, this first column corresponds to the pivot variable. That means k2 is the free variable. So we can set it to whatever we want, say 1, and then k1 equals minus a half. You can multiply it by any scalar to get nice whole numbers, which we usually try to do. So here's a nice eigenvector corresponding to lambda 1, which was 0. Okay, now let's do for lambda 2, which is 3. We'll do 2 minus 3 and 1 minus 3. Get a minus 1 and a minus 2, and the others stay the same. You can see that the second row is a multiple of the first. It better be if there's only 2 rows, because we want a row of all zeros. There's a pivot column. So here's the free variable. This top line tells us k1 minus k2 equals 0, or k1 equals k2. So just set k2 equal to 1, and there you go. There's a basis for the null space, or it's the solution to we found the 2 k's that correspond to these 2 distinct eigenvalues. And by the way, do a test if we have distinct eigenvalues. First, if there's just 2 of them, here's the linear combination we're looking for. Is this thing equal 0 only if these 2 c's equal 0? Well, we can multiply everything by a, right? And I'll still get a 0 on the right. And a times the k, that's the lambda times k. K1 corresponding to lambda 1, K2 corresponding to lambda 2. Okay, I've got that equation and that equation. I'm going to multiply this top equation by lambda 2 and then subtract it from this equation. There it is. And when you simplify it, you get this. We just said the eigenvalues are distinct, so lambda 1 minus lambda 2 is not 0. The eigenvector itself is not 0. That forces C1 to be 0. If I did similar algebra I think if I make this lambda 1, I'll find that C2 must be 0. And you could keep doing that for any number of eigenvectors, and you'll find that that means they're independent. So eigenvectors that correspond to distinct eigenvalues are linearly independent. I'll talk about repeated eigenvalues and their corresponding eigenvectors in the next video.